The following is a brief presentation of new acid mine drainage treatment technology developed and patented by HPT Research Incorporated. The site selected for the AMD pilot plant demonstration is the Mammoth Mine Complex, located on the side of a mountain above the western shore of Shasta Lake in Northern California. The Mammoth Mine, actively worked from the late 1800s until the 1930s, was primarily involved in the recovery of copper, zinc, and gold. The drainage presently flowing from the mine is highly acidic and contaminated with heavy concentrations of toxic metals that flow directly into Shasta Lake. HPT's new AMD treatment process will reduce contaminant levels well below present discharge limit. In fact, the quality of the final treated effluent from this site exceeded federal drinking water standards. Unlike conventional lime AMD treatment processes that produce mountains of hazardous lime sludge, the HPT technology utilizes ISM reactors, producing relatively small volumes of pure metal hydroxide sludge. All of the equipment used for the pilot plant demonstration was mounted on mobile trailers and hauled to the site. It took 4 men approximately 4 hours to set all of the equipment up, approximately another 20 minutes of calibration before the system was producing clean, clarified water. In addition to removing all of the contaminants, this pilot plant demonstration proved the flexibility and adaptability of the system design. During the 2-week run, rainwater intrusion changed the chemistry of the influent stream, but the equipment automatically adjusted for these changes.
About 20 gallons a minute.
We're at the Friday Loudon portal of the Mammoth Mine in Redding, California. This is the area where the acid mine drainage is coming out of the bottom of the mountain here. Back inside about 600 feet, there's a large concrete structure that is blocking, preventing all of the water from coming out. As a result, it has risen to approximately 350 feet inside the mountain, creating about 190 pounds of pressure at this point right here. We've hooked up a valving situation coming out of the bottom of the portal, running it through a hose, which we're controlling the flow rate, and into a surge tank. This is where we're starting our treatment. This is the raw influent from the mine that we're treating. We're using this 500-gallon tank as a surge tank. This is storage of the acid mine drainage. Within the tank, we've got a large influent pump controlled with a flow switch in there. The level of the water within the tank falls, the system is automatically turned off in the trailer. As long as the flow switch is up, we've got water flowing into our processing equipment. Right here at the rear of the trailer, we've got an influent filter. This is here just for a safety factor to catch any debris that might be in the water. Yeah, as you can see, we've got quite an array of plumbing manifolds. All of these things are connected together and do various things. What we're going to start with here are some of our pH meters that are registering the pH of the material coming in. The manifold system into a second mixer injector system, and that's raising the pH to between 7.5 and 8. Now the water has gone through these things. It's been pre-treated with the additives. It's gone through the ISM reactors and then goes into the clarifier. They're supplied with a DC power unit up here. And we use varying voltages depending upon the waste streams we're working on. the water goes through the reactors, through the last mixing chamber, goes into the clarifier. We're adding a polymer flocculant at this point. Polymer flocculant grabs all the small particles, pulls them together in a heavy group, and they precipitate to the bottom. We'll take a sample out of this right here. This represents the treated influent prior to entering the clarifier. As you can see, there's quite a bit of solid material within this sample. As the polymer reacts with the treated material, you get a separation. Does that show up right there? All the clarifiers do is separate the solids from the water. So here we're looking at the top of the clarifier. What you see here is the dirty water side flocculation chamber. Water goes down in the clarifier, separated by a large baffle that goes all the way to the bottom, and your clarified finished product comes up on this side. This is the water that's being discharged right here. Now we have removed all of the heavy metals at this point. We've adjusted the pH, and this water is sufficiently clean to discharge. In most instances, this not only meets discharge requirements, but either meets or exceeds federal drinking water standards. We have eliminated all the metals from it, and it is now clean enough where you can drink it. Perfectly clean. Okay, in this particular test, we were able to run the system using two clarifiers in parallel. We were able to double the output. And this clarifier is doing the same thing as number one clarifier doing. It's merely taking the pre-treated water, separating the solids, producing a clear fluid on this side. Now, periodically, we have this set up so that the sludge from the bottom is automatically pumped out. And it goes into a holding tank outside. And this we further treat. Demonstration trailer. And adjacent to the trailer outside here is the storage tank, the cold storage tank, where we deposit the sludge coming out the clarifier. This is used prior to running it through the watering process. Okay, outside here, this is the filter press. These are made by HPT Research. What this does, it takes the liquid sludge that generally runs at around 1% solid, filters it through the filter plate, discharges the clean water, and we come out with a solid cake. We greatly reduce the volume of hazardous material that has to be discharged. Perfectly clean.